Okay, so hi, we're going to be talking today about rolling motion. In the previous class, there were some homework questions asked, and I saved the notes from that, so I'll put those up on the Edline in case you had some homework questions. I think it was 44 and 47, and there was one more that we looked at. And that'll free us up to spend some more time on rolling motion, so that's what I really want to focus on today. Our story so far has been that if we have an object that is moving, then it has two different ways in which it can move. One of those is to translate, and the other is to rotate. In the full sense of the way physicists think about this, how many different directions can you move in?
3.
Yeah, there are 3 dimensions. We call those the 3 degrees of freedom for the object as it translates. Then, how many dimensions can it rotate in? Well, it can rotate in this way,
3.
or this way, yep. Well, let's see, which one, 2 I did? I did this one, I did this one, and then I could do this one, right? And so there are 3 axes of rotation, or 3 additional degrees of freedom, for a total of 6 degrees of freedom that an object has to move in. So you could actually have 6-dimensional motion. It's not really, but it seems that way. So our total kinetic energy is the sum of the translational and the rotational. And what I said yesterday is that in general, for general objects, these two are generally independent of each other.
But in this case, they're not.
But in one special case, they are not independent of each other, and that is when the object is rolling without slipping. If the object is rolling without slipping, then what happens is that points on the circumference of the object roll along and grab the surface that they are rolling on. You remember that we used what kind of friction for objects that are rolling without slipping? What flavor of friction did we use?
Kinetic.
And why kinetic?
Because it's in motion.
Nope. Very important. If an object is rolling without slipping, what is the bottom of that object doing? It's grabbing and pushing off without sliding. So we do not use kinetic friction, but static friction for objects that are rolling without slipping. And likewise, as this object rolls along, then the distance that it travels like so has to be equal to the distance traveled around, which means that I really overdid this here. It should be more like this. The distance that I travel in this direction, from here to here, d, has to equal the distance around the circumference that the rolling object travels. In other words, it has to equal r delta theta. Does that make sense to everybody? In other words, if I have an object of radius r, and I take it through one rotation, and as it goes one rotation around without slipping, then it has to travel a distance of 2 pi r for one rotation. If it doesn't travel that distance of 2 pi r, then it's sliding, either backwards or forwards, as it's going. Does that make sense there? Okay. Now, because the distance traveled, maybe we can even call this delta x, is equal to r delta theta. Therefore, the rate at which the distance is traveled, namely the speed, is equal to r delta theta over delta t, or r omega. This is exactly the same equation that we had before for objects along the for objects that are in motion, that are rolling. But now there's a significant difference, because the velocity that we're looking at right here is not just the velocity of points along the circumference, but also the velocity of the center of mass. This is crucial. As the object rolls along, its center of mass goes with it, so that the velocity of the center of mass is equal to, I should say the speed of the center of mass is equal to the speed of the points on the circumference, which is r omega. The velocities are not quite the same because the direction of that velocity will depend upon where the point is on the circle. If the point is on the bottom of the circle, then that velocity will be backwards, right? If the point is on the top of the circle, then that velocity will be forwards, and if it's on one of the sides, then it will be up or down. Nevertheless, the speed of the center of mass will be equal to r times omega. Now, what sort of implications does this have for us? Well, I'm going to take a look, first of all, at one of the homework questions, which was the spool question. I think that was 44. Where the guy has the spool, and he's hanging out some cable on it. 40.
No, that's not physics. It's physics.
68. That's it. Sorry about that. The other class I drew the fellow with an impossibly large neck.
That's pretty large.
We need to make this horizontal, otherwise it gets too complicated. Okay. So this fellow has a hold of the spool, and now what he does is he grabs the rope and he walks a distance of L. And so they ask how much rope comes out of the spool, and how far does the center of the spool travel? Now, at first your thought is L. Then you realize, no, that's not right, because the rope gets longer, doesn't it? And if the rope gets longer, then the spool can't be going L, because if the spool went L, then the rope would stay the same length. So L isn't right.
The spool's not moving.
The spool can move.
Is it moving? It's moving the other way.
He intuitively thinks that it's going to be half of L. So you envision that the spool is going to go L over 2, like so, and then the rope will get longer by L over 2. So that the amount of rope that we pay out is L over 2. Huh. That's his intuition. Does that make sense to the rest of you?
Wait, okay, so the guy moves the length of L?
Guy moves the length of L, he grabs the string, he walks the length of L, and intuitively we understand that the rope should get longer as he goes, right? Because it's going to start flowing out. But also the spool is not going to stay put. It's going to start moving as it rolls.
I think it's like 1/3. It's moving like 1/3.
Okay, so she's thinking, what, 1/3 and 2/3 or something like that?
I think like the spool moves like the length of like 2/3 or 1/3, and then like the string gets like to 2/3.
Okay.
I don't know what I'm like. You know, like 1/3. Like it moves 1/3 of the how much.
Yeah, I understand what you're saying. Does anybody else have opinions on this?
The string coming out of like the top.
Strings coming out the top. Well, if it moves L, if the string comes out L, then that means that the spool itself doesn't move at all. Because the man is moving a distance of L, so if he pulls out L's worth of string, now the string is L longer than it was before, which means that the spool has to be back where it started. So this scenario would look like this. The man grabs the string, and he stretches it a distance of L, And if we call this D to begin with, then that's D also, right? So that now the spool has not moved. The center of mass has not moved.
It's stretchy.
No. String comes off of the spool. So that the string, the length of string that is off of the spool now gets longer. We need a spool. to see
You
this.
need a
Where's the string?
I got.
We have string and spool.
I'm in the string.
Aha, we have string.
I'm a screwdriver. I went and grabbed a screwdriver and grabbed it out.
We could maybe use a ball as a spool. Good? Yeah, yeah. Okay. So let's do scenario
Well, how
one.
long is the string out?
That is it.
So here we have a screwdriver with string wrapped around it. And what I'd like for you to do is to just sit there. Yeah, that's great. Just sit there. And I'd like for you to let the screwdriver rotate as I walk backwards, okay? So here I am. And if we mark this spot
Well,
right
it should be flipped over the other way.
No matter, no matter. So if we mark this spot right here on the string. Now I pull back like this. As I pull back, then the length of string that comes out is exactly equal to the distance that I pull back,
Except the thing rotated a
Has to
whole
be.
bunch more.
right? Now this thing rotated in place to make that happen. Okay? Now let's wind it back up and do it differently. This time, what I'd like for you to do is to go with it a little bit.
You want to screwdriver?
Off the screwdriver, that's right. I think it can go down. Okay. So now that as I pull it, he comes towards me, and the distance that he travels plus the distance that the string pays out is equal to the total distance that I move backwards.
So yeah, I think like the spool moves 1/3 and you move 2/3.
It's equal to each other.
Equal.
I still don't understand. Okay. So split the motion up into two pieces then. Rotation plus translation, right? For the rotation, we get a certain delta x. For the translation, we get an additional delta x. Those two add up to the total distance traveled. That's it. That's all. So that if the rotational delta x is L, then the translational delta x is necessarily 0. Because the whole distance is 0. Okay? Now, let's take Ben's insight. That the distances have to be the same. Why is that? Well, let's actually compute it. How much string pays out? Let's call this the delta x for the rotation, and let's call this the delta x for the translation. And those two add up to L. The delta x for the rotation is going to be the amount of string that comes off, and the amount of string that comes off the top there is going to be equal to the radius times the angle that we turn, that the spool turns. Meanwhile, the delta x of translation is the delta x of the center of mass. And as we have already seen, that is equal to r times delta theta as well. So that the total, which is L, is equal to 2r delta thetas, and r delta theta is equal to, therefore, L over 2. The spool moves by L over 2, and the rope increases in length by L over 2, and then is exactly correct.
So
Question?
So, I'm just a little bit confused.
Okay. Well, if you think of it, let me know. So as I said, we're talking about rolling without slipping, and what we've discovered is that the velocity of the center of mass of an object that rolls along is the same as, the speed is the same as the speed of an object on the circumference. In other words, it is r omega. So that if I have an object that is rolling along here, so that it goes a distance d, like that, and as it rolls along, it is going to have a kinetic energy that is dependent upon the speed only. In other words, objects that roll without slipping have their rotational and translational kinetic energies linked together. Let's see why that is so. We know that the total kinetic energy is equal to translational plus rotational. And we already know the expressions for both of those. 1/2 mv squared for the translational and 1/2 I omega squared for the rotational. And now here's the key move. Because my object is rolling without slipping, I know the value of omega. Omega is equal to the velocity divided by the radius. And that means that I can substitute directly into the omega expression right here. And when I do, I get an expression that is a function of only the velocity without the angular speed being visible. So when we have a rolling without slipping case, my angular velocity is tied to the linear speed of the object. Does that make sense to everybody? That,
So what equation did you start with then? For the,
here.
that was the thing at the top.
And then I substituted in the fact that we're rolling without slipping, so that the velocity of the center of mass is the same as r times omega.
So omega is only d over r when you're talking about roll.
Without slipping, right. If you're rolling with slipping, for example, if your tires are in snow and they're like this, then your omega is going to be greater than v over r. And if you are kind of dragging, so that you're sort of skidding along, then your omega will be less than v over r. But if your wheels are actually grabbing it, going with it, rolling with it, then your omega must be equal to v over r. Now we can actually go a little bit further in the case of common objects that roll. What shapes of common objects typically roll? Wheels. What type of object would you model a wheel as?
Tire.
Okay, but in terms of your, table that you have,
Cylindrical.
cylindrical, but what type of cylinder?
It's a hollow.
Is it more hollow or solid?
Solid.
That's tough. Most wheels are solid. Some of them have a lot more mass to the outside. So you might have to do something fancy with it to find out the eye. But if you consider just sort of wheels that we have on our lab cart that are just sort of solid aluminum, then we can take, for a solid wheel, cylindrical wheel, then we can replace now the moment of inertia with what expression? Yeah. Now be careful about that because we already have a factor of 1/2.
Is that fourth?
Uh-huh. That's exactly it.
Which way? So It's rotating, so it's that going positively in this direction.
Yes, that's right. And the kinetic energy, by the way, doesn't care about direction. Right? When you square your omega, any plus or minus sign goes away. So two lovely things happen. The first is that my r squareds cancel in this expression, just like that. And the second is that a half times a half is, as Andrew observed, 1/4. So that I actually get 1/2 mv squared as the translational component of my kinetic energy, and I get 1/4 mv squared as the additional rotational component. Because the wheel is rotating, it has more kinetic energy than an object that's just sliding. And what is 1/2 mv squared plus 1/4 mv squared?
Is that like
3/4 mv squared, that's right. So that the total kinetic energy of a solid wheel that is rotating, rolling without slipping, is actually 3/4 mv squared, greater than 1/2 mv squared because of the additional rotational motion. Same thing can happen with our other common rotating object. What other kinds of objects rotate? Balls, which are I need a name for it. Spherical, that's right. So if I have a solid spherical ball, then my k-tote is once again 1/2 mv squared plus 1/2 I omega squared. But now the I expression is different because I have a solid sphere instead of a solid cylinder. According to your chart, what is the moment of inertia of a solid sphere? Yep. So I can substitute for the I. And again, because I am rolling without slipping, I can substitute V over R in for omega. Here's my rolling without slipping condition. And when I clean all this up, halves go away, my R squareds cancel, and I get just V squared left behind. What is 1/2 mv squared plus 1/5 mv squared? 7/10 mv squared. So that a solid sphere that is rolling along is going to have a total kinetic energy of 7/10 mv squared. Half of that from the 1/2 mv squared from translating, and the additional 1/5 from the rotational motion. We think now about our ping pong ball, which is actually a hollow sphere, but we remember that the ping pong ball has additional translational energy when you put additional kinetic energy of rotation when you put topspin. And when that ball with topspin hits, then it converts into translational and off it goes. Okay? Now, how does this actually work out in practice? Here I'd like to consider the following problem. A solid sphere of mass m is placed at the top of a ramp with height h. It rolls without slipping to the bottom. How fast is it going? And then I want to compare to the speed of an object that slides down without friction. Now we want to be clear about something. What we want to be clear about is that in the rolling without slipping case, there is definitely friction involved. And how do we know this?
Because it's not slipping.
Because it's not slipping, that's right. And what type of friction is it?
Static.
Static friction, exactly. Because the point of contact, right where that ball, that sphere, meets the ramp, is going to be not in motion. Okay. So here we go. Let's work the first problem. have a mass M right here. Any suggestions about how we might proceed?
Label.
Got some labeling going on. Yep, yep.
But, oh, heights, speech, I meant like,
Data is not given, interestingly.
before, after,
Before and after, what are you talking about?
like the kinetic,
Energy
energy.
Energy accounting is what we're talking about. That's right. So let's identify a before and after place. Where's our before going to be?
Where it is.
And where's the after going to be?
Bottom.
All right. Good. And now give me an energy accounting. What do we have?
Plus one after there. Plus one
MGH.
past I.
Let's have a format.
Stop, don't say W.
MGH.
What are you talking about? What's that called?
Potential.
Potential. Right. So we want to take a look at potential, and we want to take a look at
Kinetic.
kinetic. And here, because there are two components, then we have to consider both translational and rotational components of our kinetic energy. All right? Before, fill in the table here. MGH, right? Translational? Mhm. What is the velocity in the before situation?
Zero.
All right, so what is the kinetic energy? Zero. And rotational? Zero also, because it's not rotating. So that my total before is MGH. Okay, after we reach the bottom, what is my potential energy?
Zero.
What is my translational energy?
1/2 MV squared.
Okay, and what is my rotational?
One I alpha
It's 1/2 I
square.
Omega.
Omega.
omega squared, right?
Normal. Exact.
Where's the W? You can choose between those.
All right, but now we need to use the fact that we are rolling without slipping. And because we are rolling without slipping, what can I do?
Right. I.
V equals R delta theta.
No.
2/5 square. Well,
Because I'm rolling without slipping, what is the big idea of today's lecture?
Omega equals delta theta over delta 2.
No.
Becomes equal to R omega.
Right. V equals R omega. In other words, omega is equal to
Omega is equal to
V
over R.
V over R. Exactly. So then I'm going to replace omega with V over R, and I'm going to replace the I with the appropriate I for our object. What is the appropriate I for our object?
2/5 MR squared.
2/5 mr squared.
But we're not gonna have to know those, right?
Correct. And now watch the algebra here. My 2's cancel, my R squareds cancel, and what I get is 1/5 of mv squared is the total expression for the k rotational. When I add these up now, let's move this guy to here. When I add these up now, 1/2 mv squared plus 1/5 mv squared is 7/10 mv squared. And there you go. Okay? I've identified energies in before and after states. Now what? So equal to each other, he says. I agree. Keep going.
You cancel out the atoms. Most of them. Square root the other side. And then you have
Tell me what I got.
to get rid of 7/10 on the right side. No,
I can't get rid of. Get rid of is not
change it, make it to
mathematical.
the other side. So
I can't make it to the other side.
divide both sides by
Like
7/10.
Good. Dividing by 7/10 is the same as multiplying by what? 10/7. So what do I end up with?
Square root of
10/7.
There you go. And there's my speed. Okay. let's come back and answer the second question that was asked, which is, let's compare this to the speed that an object would have if it were only sliding. So again, we have a before and after scenario. Here's our before, here's our after. What does our chart look like now?
Just the same without.
Exactly so. So I have U and K trans, but my K rote is 0.
So we can just do V is 2G.
Yeah. I think you forgot a root in there.
Just go to 2GH.
So we end up with this.
2GH.
The total energy is again equal to mgh. And the total energy here is 1F_mv squared. And so when I set them equal, I can again cancel the common factor of m. And now I get root 2gh. How does this compare to the speed that we had for our rolling object? Which one's larger? The bottom one is larger, that's right. 10/7 is about what decimal?
1.1.
It's 1.4 something, right? So 1.43 is actually correct. So 1.4 compared to the factor of 2 there. Why is the rolling object going slower? No, it's rolling without slipping.
Oh. The rolling one, because it can just, continue on its merry way, where the slide one is just kind of much like, I don't know, never mind. It's in my head.
Well, instead of have it being in your head, have it be in the math. Use the math to explain it.
You don't have another factor.
And you don't have the K row. The K row.
There's no what's it called, static friction?
Okay. Yeah, that's one way to think of it. There's no force of friction pushing back. Yes. That's one good answer to the question. The object that is rolling without slipping has to experience a static frictional force pushing back on it. And therefore, that static frictional force reduces its acceleration. That's a great one.
So why is pushing the rolling things pushing?
Because there's another factor.
Yes.
Because there's
Great question. Why is pushing rolling things easier than pushing sliding things?
Most platforms always good. There's the friction spot.
It's gravity.
Not gravity. I said it's gravity and
It's gravity.
1 degree friction.
Yes, but the question is, why is it easier to push something that is rolling than it is to push something that is sliding?
Less surface area.
Yeah. A lot less surface. Yeah. Good.
Yeah.
Because it's already in motion, like it's already like at a faster motion.
Here's something else that's really interesting. If you push something that's rolling, then that static frictional force does not take away any kinetic energy. It simply converts it into rolling motion. Right? That's what we saw. Energy is conserved in both cases. But if you have an object that's actually sliding, that sliding friction is literally taking away energy and just throwing it away as you go.
But I thought you said they were conserved.
How are those pulleys doing that?
Converted it to heat. And then
Good. All right. So I think we've had enough. We'll call it a day.